All right, so let's continue. Now, let me start with the following question. So, corollary number 2, the result we just proved, basically, and the example shows that, whenever you have primal dual pair of LP problems, if one problem is unbounded, the other problem is infeasible. Okay, so that's important. If the primal is unbounded, then the dual is infeasible. If the dual is unbounded, then the primal is infeasible. So the next question is the following. So, we know that if one problem is unbounded, the other one is infeasible. So what can we say in the case that for example, suppose that the primal problem is infeasible? Can I say that dual problem should be unbounded at the same time? So in other words, is the reverse implication also true? So if a problem is unbounded, the dual is infeasible. If the problem is infeasible, then is the dual unbounded? So is it like an if and only if statement? So that's a question that we're going to look at now. So if an LP problem is infeasible, if an LP problem is infeasible, is its dual always unbounded? So in other words, basically, is the reverse implication also true? So we know that if a problem is unbounded, the dual problem is infeasible. The question is, if the problem is infeasible, is the dual unbounded? So, and the answer turns out to be no, actually. Here's an example. So here's my primal problem. I want to maximize x1 plus x2 subject to x1 minus x2 is less than or equal to minus 1, and minus x1 plus x2 is less than or equal to minus 1, and x1 and x2 are non-negative. So suppose that this is my primal problem, okay? So we have two less than or equal to constraints and two non-negative variables. I claim that this problem is infeasible, basically. So I claim that this problem cannot have a feasible solution. Does anyone see why that's the case? So essentially, I'm claiming that this problem is infeasible. Well, there are two ways of saying this, basically. Constraints. Exactly. So for example, if you look at the first two constraints, okay? Now just ignore the non-negativity constraints for now. So anything that satisfies these two should also satisfy the sum of these two inequalities as well, right? So if you sum these two inequalities, the left-hand side becomes 0 because x1's cancel, x2's cancel. So you get 0 less than or equal to minus 2, but that can never happen, right? 0 is less than or equal to minus 2. So as a result, this problem cannot have a feasible solution. Okay? So what about the dual problem? So let's construct the dual problem now. Again, I have two constraints, so I need two variables, w1, w2. So what's the objective function of the dual problem? Minus w1, minus w2, basically, right? So minus w1, minus w2. What does the first constraint look like? w1 minus w2. Okay? w1 minus w2. So we have less than or equal to constraints. We have greater than or equal to 1. And if I look at second column, I have minus w1 plus w2. Minus w1 plus w2 is greater than or equal to 1. And w1 and w2 are non-negative. So this is my dual problem. Okay? And I claim that the dual problem is also infeasible. Why is that? Again, by the same reasoning. So if you just take these two constraints and if you add them up, the left-hand side becomes 0, the right-hand side becomes 2, but 0 is never greater than or equal to 2, right? 0 is not greater than 2, so as a result, you cannot satisfy these two constraints at the same time, so which means that the problem is also infeasible. So as a result, in corollary number 2, we said that if a problem is unbounded, its dual is infeasible. But this example shows that if a problem is infeasible, its dual is not necessarily unbounded. Okay, its dual can also be infeasible at the same time. So as a result, if we start with an infeasible problem, then the dual can be either infeasible or unbounded, basically. Okay, so these are the only possibilities. Let me write it down. So if an LP problem is unbounded, its dual is always infeasible. Okay, so that's important. That was corollary number 2. If an LP problem is infeasible, then its dual is either infeasible, such as this example, or unbounded, which is the previous example. So if you start with an infeasible problem, then if you take the dual can be one of the two things. It can be either infeasible, or if you look at the previous problem, so think of this as your primal problem. Okay? So you start with an infeasible problem. Its dual is unbounded in this case. Okay? So as a result, these are the only two possibilities. So if you start with an infeasible problem, its dual is either infeasible or it has to be unbounded. Okay? But if you start with an unbounded problem, its dual is always infeasible. So that's important. Okay? So is this clear? Any questions? All right, so then now we're going to prove one of the most important theorems in this course. So this is known as strong duality theorem. Which I'm going to abbreviate as SDT. So let's just pause for a second and let's try to see the steps that we have sort of taken so far. Now we started with a primal dual pair of LP problems. Okay, primal is a maximization problem, dual is a minimization problem. And on the real line, we showed that the primal problem is trying to make Cx as large as possible. Okay, and the dual problem is trying to make WB as small as possible. So in some sense, they're actually playing games. So this is the primal problem. This is the dual problem. Okay. And then we said that Cx is always less than or equal to WB. So the objective function value is always, primal objective function value is always less than or equal to dual objective function value. And we also said that if they happen to be the same, then they should be optimal. Okay? So here we're going to show that actually they are always the same at the optimal solution. Okay? So now we're going to actually show that the optimal values of the primal and dual problems are always the same. Okay? They always meet at the same point. So we're going to prove that result. This is known as strong duality. Consider the following pair of primal dual LP problems. Primal dual LP problems. So here's my primal problem. And then I have my corresponding dual problem. So now what we're going to do is we're going to show that actually the optimal values of these two problems are always the same. Okay? So in other words, we're going to show that they always meet at some common point. The Cx value and WB value always meets at the same point. So if any one of these two problems, if any one of these two LP problems has an optimal solution, so does the other one. So does the other one, and the optimal values are the same. The optimal values are the same. Furthermore, if B is an optimal basis for the primal problem, of course, this is after adding slack variables. Then the solution given by W star, which is equal to CB times B inverse. And if you recall, I told you that this was important when we discussed simplex method. So it turns out that W star computed in this way turns out to be an optimal solution of the dual problem. Okay, so W star, which is a 1 by m dimensional vector, or an m-dimensional row vector, is an optimal solution of D. So this is a really important result, basically. It tells you a number of things. So first of all, it tells you that whenever you have primal dual pair of LP problems, if at least one of them has an optimal solution, okay, then so does the other one. So that's the first implication. Okay, that's the first result. So which means that, for example, if the primal problem has an optimal solution, then the dual problem cannot be infeasible, basically. Okay, it has to have an optimal solution as well. Secondly, it says that if I look at the corresponding optimal values, they're actually precisely the same. So this value and this value actually meet at some common points. Okay. And the third result is the following. So if I know of an optimal solution for the primal problem, and if I know the corresponding optimal basis, then I can compute an optimal solution for the dual problem as well, as a function of that. Okay? So if I have an optimal solution of the primal problem, then I can immediately find an optimal solution of the dual problem as well. And that's given by CB times B inverse. Remember, CB is the cost coefficient of basic variables, and B inverse is just the inverse of matrix B. Okay? So as a result, if I have an optimal solution for the primal problem, then I can immediately compute an optimal solution for the dual problem as well. Okay? So we're going to prove this result. And the proof actually uses the simplex method. Okay? So what I'm going to do is the following. So let us add slack variables to the primal problem. So that we convert it into standard form. So that we can apply the simplex method. Okay. So remember, we just need a slack variable for each constraint. The primal problem has less than or equal to constraints, so I just need to add slack variables, one for each constraint. And let x star be given by xp star xn star be an optimal basic feasible solution for the primal problem. So we know that xn star is necessarily equal to 0, and xp star is given by b inverse times little b. Okay, so that comes from the definition of a basic solution. And of course, by feasibility, b inverse b should be non-negative, right? So now what I'm going to do is I'm going to go ahead and try to construct the simplex tableau corresponding to the solution directly. And we have seen before that we can do this, right? If I know a basis, I can go ahead and construct the simplex tableau corresponding to that solution. Okay? So we have done that before. So let us construct the simplex tableau corresponding to this solution. This basic feasible solution, okay? Well, this is already in your notes, but let's try to remember this. So I have my z, objective function value, variable. Then I have my original decision variables x. Then I have my slack variables, which I'm going to call xs. So xs, think of them as the slack variables to turn these into equality constraints. And I have my right-hand side value. Well, since we derived this already, I'm not going to go through the details, but we know that the simplex tableau essentially looks like the following. So I have one here. Here I have CB times B inverse times A minus C as the row zero coefficients of the original variables. Here I have CB times B inverse. And the right-hand side is given by CB times B inverse times little b. Okay, so these are the row zero coefficients. Then I have my basic variables, which I'm going to call xp. I have zeros here. Over here I have b inverse times a. Here I have b inverse, because remember, under the static variables we had just identity matrix. If we multiply from the left, we just get b inverse. And the right-hand side becomes b inverse times b, which is precisely the values of my variables, which is exactly the same as the current solution, basically, okay? So what do I know? I know that this solution is optimal, right, for my primal problem, okay? So I'm assuming that x star is an optimal solution, and this is the simplex tableau corresponding to that optimal solution. So now this is where you should sort of start thinking about the simplex method. So remember, primal is a maximization problem. So this is the tableau corresponding to this solution, and we know that this is an optimal solution, okay? So how do you check optimality from the simplex tableau for a maximization problem? Well, we look at row zero coefficients, basically, right? And for a maximization problem, what should we be looking for? So if there's a negative variable, if there's a negative coefficient, sorry, then that variable actually will increase the objective function value, okay? And since we have an optimal tableau, then that means that all row zero coefficients should be non-negative, basically, right? Okay? So let me write that down. So since this tableau is optimal, all row zero coefficients should be non-negative. So remember, if this is not true, then that means that there is another entering variable, and I can further improve the objective function, right? Okay, since I'm assuming that I already have the optimal solution, then this tableau should be optimal. So which implies that if I look at the row zero coefficients of the x variables, which is cb b inverse a minus c, should be greater than or equal to 0. And of course, please keep in mind that this is actually a vector, right? So number of components here is the same as number of original variables, and number of components here is the same as number of original variables as well. Okay, so this means that each component should be non-negative. And CBB inverse, which is another vector, that should also be non-negative. So before I move on, is everybody happy so far? So is everybody following? Okay. So I'm just making a simple observation that, by definition of the simplex method, if this solution is optimal, then all row zero coefficients should be non-negative. And I'm just writing them as inequalities, basically, okay? Any questions so far? Well, if you look at your notes, this was a simplex tableau corresponding to a basic feasible solution. We did this before, okay? All right. So now what I'm going to do is the following. So let W star be defined as CB times B inverse. So what I want to do is the following. I want to show that this solution, first of all, is a feasible solution of the dual problem. And then I want to show that this solution is not only feasible, but it's actually optimal for the dual problem as well. Okay? Because remember, if you look at the statement, it claims that this is an optimal solution of the dual problem. And to show optimality for the dual problem, I need to first show that it's a feasible solution. And then I need to show that, somehow I need to show that that is the best feasible solution, okay, for the dual problem. All right, so now let me continue from here. So if W star is equal to CB times B inverse, then this implies that, so instead of CB B inverse, I can actually just write W star, okay? So W star times A minus C is greater than or equal to 0. Right? So if I just look at the first inequality, this is essentially the same as this one. Are you still with me?
Yes.
Okay. Well, so this is essentially the same as W star times A is greater than or equal to C, basically, right? Okay. Well, let me just go back to my dual problem. So I have W star times A is greater than or equal to C exactly, right? So that means that I satisfy these conditions. Okay, my W star satisfies these constraints, so that's nice. Secondly, if I look at the second inequality, well, this is precisely the same as W star, so W star is non-negative basically, right? So this implies that W star is also non-negative. So W star times A is greater than or equal to C. W star is non-negative, so this implies that W star is a feasible solution for the dual problem. Okay? So if you look at the dual constraints again, W star times A is greater than or equal to C, W star is non-negative, so that means that all the constraints are satisfied. Okay? So this implies that W star is a feasible solution of the dual problem. So that's nice, okay? But I want to show more than this, right? I want to show that W star is not only feasible, but it's actually an optimal solution of the dual problem, okay? So how am I going to show that? Well, so let me look at the objective function value of the primal problem, okay? So that's equal to C times X star. Okay? But I know that I can write this as, basic and non-basic variables. In terms of basic and non-basic variables, I have CV times XP star plus Cn times Xn star, right? So if I separate into basic and non-basic components, so this is what we have. What do I know about Xn star? So Xn star are the non-basic variables. Their values are equal to. What are the values of non-basic variables? 0, exactly, right? So as a result, the second term actually disappears, right? Is everybody following or? Okay. So the objective function value of the primal problem evaluated the solution X star is actually given by this CV times XP star, right? Okay. What do I know about XP star? Well, XP star has an expression over there, which is given by B inverse times little b. Okay, so as a result, this is the same as CB times B inverse times little b. And that should be surprising, and that's indeed the right-hand side value of the objective function, right? Okay? But we know that X star is an optimal solution for the primal problem, right? So as a result, this is precisely the optimal value of the primal problem. Right? So this is the optimal value of P. All right. Well, I have again CVB inverse that shows up in that expression. And I know that CVB inverse, I define it as W star. Okay? So I'm going to make that substitution. So I get W star times B. Well, so X star is a feasible solution for the primal problem. W star is a feasible solution for the dual problem. And the objective function values are the same. Okay? So the primal objective function value is the same as dual objective function value. So which means that we have a pair of solutions for which the objective function values are the same. Okay? So now we're going to use the previous corollary, right? So by corollary number 1, W star is an optimal solution of D. And that actually finishes the proof, okay? So that shows that indeed W star is not only feasible, but it's actually an optimal solution of the dual problem. So this was the reason why I told you earlier that CVB inverse is an important quantity, and the importance comes from this one, okay? So remember, CVB inverse can be read directly from the row zero coefficients of the slack variables, okay? So we've discussed this before. So as a result, if you solve the LP problem using the simplex method, the primal problem, then you can actually read the solution for the dual problem directly from the simplex tableau. Okay, that's important. Any questions about this proof or the result? Well, then here's a summary between the primal and dual problems, the relationship between the primal and dual problems. If the primal problem has an optimal solution, okay, then by the strong duality theorem, we know that the dual problem also has an optimal solution, okay? So then dual is also optimal. And this is an if and only if statement, okay? So the primal problem has an optimal solution if and only if dual has an optimal solution. Which means that whenever any of these two problems has an optimal solution, so does the other one, okay? That's important. If the primal problem is unbounded, then what does that imply about the dual problem? Infeasible, exactly. So unlike the first one, this is a one-sided implication though, okay? So if you have an unbounded problem, then dual problem is infeasible. If you have an infeasible primal problem, again, this is a one-sided implication, so we get either unbounded or infeasible dual problem. And of course, since primal and dual are symmetric, you can also treat this as the dual problem and this as the primal problem as well, okay? Okay, so as a result, this is the full relationship between the primal and dual problems. If any one of them has an optimal solution, so does the other one. And they have the same optimal values, so that's the first case. If any of these two problems is unbounded, the other one is infeasible. And if any of these two problems is infeasible, then the other one is either unbounded or infeasible. So these are the full sort of picture of relationships between the primal and dual problems. Okay? Questions? All right, so now let me give you an example just to illustrate the strong duality theorem. So suppose that the primal problem is given by the following. Maximize minus 3x1 plus 2x2 subject to minus 3x1 plus 3x2 is less than or equal to 6, and minus 4x1 plus 2x2 is less than or equal to 2. And x1 and x2 are non-negative. Okay? So again, we have only two variables. Let's just draw the feasible region. So the first constraint looks like the following. If x1 is 0, x2 is equal to 2. And if x2 is 0, x1 is equal to minus 2. So it goes through these 2 points. And the origin is feasible, so as a result, we have this side of the line. And the second constraint looks like the following. If x1 is 0, x2 is equal to 1. And if x2 is 0, x1 is equal to minus 1 over 2. So it goes through these 2 points. Again, the origin is feasible, so as a result, we pick the right-hand side of this line. And we have non-negativity constraints. So the feasible region is given by this area. Okay? And then you can draw the sort of isoprofit line. I'm not going to do that, but you can show that this is the optimal solution. And the optimal solution is given by 1 and 3. Okay, it's given by the intersection of the lines corresponding to these two constraints. And the coordinates of the intersection point is given by 1 and 3. Okay? All right, so what is the corresponding dual problem? So this is my W1, this is my W2. The dual problem will look like the following. It's going to be a minimization problem. What is the objective function? So 6W1 plus 2W2, okay? All right, so what does the first constraint look like? Minus 3W1 minus 4W2. Will be greater than or equal to, what's the right-hand side value? Minus 3. What about the second constraint? 3W1 plus 2W2 greater than or equal to 2, and W1, W2 are non-negative. Okay? So again, let me draw the feasible region. Okay, so what does the first constraint look like? Well, if W1 is 0, W2 is like 3 over 4. So let's say this is 1. So somewhere here is 3 over 4. And if W2 is 0, W1 is equal to 1. So 1 is somewhere over here, so it goes through these 2 points. So this is 1 and this is 3 over 4. So which side should I pick? Is the origin feasible? Yes, it is feasible, right? So 0 is less greater than or equal to minus 3, so I'm going to pick this side of the line. What about the second constraint? Well, if W1 is 0, W2 is equal to 1, so it goes through this point right here. And if W2 is 0, W1 is equal to 2 over 3, which is somewhere over here, so it goes through these 2 points. Okay? And once again, the origin is the origin is not feasible. So I'm going to pick this side of the line. So as a result, this is my feasible region, this small triangle. And once again, you can draw the isoprofit line or isocost line, and you can see that the optimal solution is given by this intersection point. And the coordinates are given by 1 over 3 and 1 over 2. And for example, just to verify, if you look at the optimal value of the primal problem, so just plug in 1, 3 into the objective function, you get minus 3 plus 6, which is equal to 3. Right? So 3 is the optimal value. And if you look at the corresponding objective function value for the dual problem, just plug in 1 over 3 and 1 over 2 into the objective function of the dual problem. So you're going to get 6 times 1 over 3, which is equal to 2, plus 1, and that's also equal to 3. Right? So the optimal values should be the same. So what I'm going to do is I'm going to just look at the optimal tableau for P. For a primal problem, and it actually looks like the following. So I have my original variables x1 and x2, then I'm going to select variables x3 and x4, and then I have the right hand side value. So this is what row 0 looks like. I have 1, 0, 0, 1 over 3, 1 over 2, and the right hand side value is 3. Then I have 0, 1, 0, 1 over 3 minus 1 over 2, 1, and then 0, 1, 2 over 3, minus 1 over 2, and the right hand side value is 3. So if you just solve the primal problem with the simplex method, this is the final solution that you're going to get. This is the optimal solution. Now remember, so x3 and x4 are the select variables, right? So I'm adding a select variable for the first constraint and the second constraint as well. And just look at the row 0 coefficients here. Okay? So we have 1 over 3 and 1 over 2. And look at the optimal value for the dual problem. Optimal solution for the dual problem. It's exactly the same as 1 over 3 and 1 over 2. Okay? So indeed, if you look at the previous case, remember CVB inverse, which is a dual optimal solution, is precisely the row 0 coefficients of the select variables. Okay? So as a result, if I go back to this example again, the row 0 coefficient of select variables in the primal problem give me precisely the optimal solution for the dual problem. Okay? So as a result, CV times V inverse is indeed an optimal solution for the dual problem. Okay? And as I said, you can easily verify that the optimal value is equal to 3, and dual optimal value is also equal to 3. So just plug in this solution into the objective function, and you get again the same optimal value as well. So as a result, by solving only the primal problem, you also solve the dual problem as a byproduct, actually. Okay, so that's important. And that's actually one of the sort of reasons why the simplex method works. We're going to see this later on as well. So in a sense, it combines the primal dual problems in one stage. So it actually the method actually solves both problems at the same time in some sense. Okay? And it stops when it finds the optimal solution of both problems. So that's the sort of stopping criterion. We're going to see later on why this is the case. But the simplex method, despite the fact that you're solving the primal problem, it's actually keeping the dual problem in mind in some sense. Okay? So it's also checking the dual problem. Yes?
Can we say the non-basic variable of the primal problem is the basic variable of the dual problem?
No, we cannot say that because the primal problems and dual problems, the primal variables and dual variables are completely different from one another. Okay? So all I'm interested in is I'm saying that the row 0 coefficients of the slack variables give me the optimal values of the dual variables. That's the relationship. Okay? So there's no relationship between basic and non-basic variables for now. Basically, all I'm saying is if I look at the row 0 coefficients of my slack variables, which are 1 over 3 and 1 over 2, they're precisely the optimal solution of the dual problem. That's all I'm interested in right now. Okay? Any questions? Does everybody see the relationship? So, hopefully. Okay? So, indeed, there's a very close relationship between the primal and dual problems, and this example illustrates that relationship. So, by solving the primal problem again, you immediately get a solution for the dual problem as well. Okay? So, that's important. So, unless there are any questions, I'm going to move on then. So, all right, so now I'm going to next discuss strong duality theorem for a different form of LP problem. So this is theorem number 9. So strong duality theorem in standard form. So suppose that my primal problem is given by, again, a maximization problem. But this time, suppose that it's already in standard form. So we know how to convert the problem into standard form, right? So suppose that it's already in standard form. So what is the corresponding dual problems? The objective function value never changes. It's always WB. The constraints are given by, again, you can look at your duality tables, WA greater than equal to C. But now since we have equality, then the corresponding W's will be actually free, right? So there will be no restrictions on W's. So W's are just free variables. I'm not sure. Thank you. So this is the corresponding dual problem. Remember, the only change is that since we have equality constraints in the primal problem, the corresponding dual variables are free. Again, if you look at your duality tables, you're going to see that this is the case. So let X star be an optimal solution, be an optimal basic feasible solution for the primal problem with the corresponding basis B. So now all I'm doing is I'm just changing the form of the primal problem. Okay, the dual problem changes accordingly. Okay. So now what I'm interested in is, okay, if I have an optimal solution for the primal problem, can I still find an optimal solution for the dual problem? Okay, in this case. And the answer is yes. And actually the answer does not change either. Then W star given by CB times B inverse is an optimal solution of D of the dual problem with the same optimal value. With the same optimal value as the primal. So in other words, even if I change the form of the primal problem, the dual optimal solution does not change. It's still given by CBB inverse. Okay? And again, the proof is not that hard. So now, unlike the previous example, so we don't need to turn the problem into standard form because it's already in standard form, basically. So I can solve the problem directly. So let us consider the optimal simplex tableau for the primal problem. So I have my objective function variable z, I have my original variables x, then I have my right-hand side value. then row 0 actually looks like the following. I have 1 here. Here I have CB times B inverse A minus C. And here I have CB times B inverse times B. Again, since we did this before, I'm not going to go through details. You can just look at your notes again. So here we have Z. Here we have basic variables. Over here I have 0. Then here I have B inverse A. And here I have B inverse little b. So remember, we discussed that this is precisely what the simplex method does, right? So it actually multiplies the equality constraints by B inverse from the left, and then it tries to zero out the coefficients of the basic variables, and that corresponds to multiplying everything here by CB and adding it to original row 0. So this is precisely what you have. Okay? So by optimality of this tableau, what do I know? Well, I know that this is a maximization problem, and if the simplex method stops, then it stops for a reason. So what's the reason? There are no negative row 0 coefficients, basically, right? Yes. Okay. So by optimality, all row 0 coefficients are non-negative. Coefficients are non-negative. So this implies that CV times B inverse times A minus C is greater than or equal to 0. So once again, I'm going to define W star to be equal to CB times B inverse. Okay, just like I did in the previous case. So now all I need to do is just substitute W star here. Okay, so this implies that W star times A is minus C is less than or equal to 0. Is greater than or equal to 0, sorry. This implies that W star A is greater than or equal to C. So which means that W star is a feasible solution for the dual problem. Here, unlike the previous case, I don't care about the signs of W because I have no restrictions on the signs of W. Okay. So since I have only these constraints, W star satisfies these constraints, so W star is a feasible solution. It's feasible for D. How can I show optimality of W star? Well, just like I did in the previous case, I need to show that the primal and dual objective function values are the same. Okay? So as a result, I'm going to look at W star times B. But W star times B is the same as CB B inverse times little b. But CB B inverse times little b is precisely the optimal value of the primal problem, right? Okay? So this is the same as C times X star, basically, okay? X star was the optimal solution. So if I plug in X star into the objective function, I get just C times X star, basically, right? So C times X star is equal to CB B inverse B, right? Okay? So as a result, we have a pair of primal and dual feasible solutions. The objective function values agree. So that means that W star should be optimal for the dual problem, okay? So this implies that W star is optimal for D. So what's the sort of main message? Well, even if I change the form of the primal problem, the dual optimal solution does not change. It's still given by CB B inverse. There's one difference though. Unlike the previous case, we can no longer read CB B inverse directly from the Tableau. Okay? So you have to actually compute CB B inverse yourself. Okay? That's the only difference. If you have select variables, such as this example, then the simplex Tableau already gives you the values of CB B inverse. Okay? Whereas if your problem is already in standard form, then basically that means that you have to sort of sit down and compute CB B inverse. So that's the only difference. Okay? But the optimal value itself does, the optimal solution itself does not change. So it's still given by the same expression, which is CB times B inverse. So as a result, this is the reason why CB B inverse is an important quantity. Okay? CB B inverse actually gives you the optimal solution for the dual problem. Okay? When you have the optimal solution of the primal problem. Okay? Any questions? All right, so if not, let's just do the evaluations.